For decades, scientists thought it was impossible. The idea of beaming delicate quantum signals from the turbulent surface of Earth all the way up to a satellite speeding through space seemed like science fiction, but now that fiction is becoming reality. A groundbreaking new study shows that it's not only possible, but could revolutionize how we build the quantum internet. Let's back up a bit. We already have quantum satellites, like China's Maisha's satellite, which have done incredible things. They create entangled particles of light in space and beam them down to Earth. This is called downlink. It's been fantastic for creating ultra-secure communication keys, a process known as quantum cryptography. For this, you only need a handful of light particles, or photons, to succeed. But what if we wanted to connect powerful quantum computers across the globe? That requires a whole different level of bandwidth, a massive flow of quantum information. The downlink method just isn't powerful enough for that. So, what's the alternative? An uplink, sending the quantum signals from Earth up to the satellite. For years, this idea was dismissed. Scientists believed the signal would be too weak, lost in the atmospheric interference, scattered by turbulence, and overwhelmed by background light from cities and even reflections from the moon. It seemed like a non-starter. Imagine trying to hit a tiny fast-moving target 500 kilometers above you traveling at 20,000 kilometers per hour. Not just with one beam of light, but with two from separate locations on the ground and having them arrive at the exact same nanosecond to interact. It sounds impossible, but a team of scientists, led by Professors Simon Devitt and Alexander Solntsev from the University of Technology, Sydney, decided to take a second look. They built a detailed computer model, factoring in all the real-world problems: atmospheric haze, sunlight, misaligned optics, everything, and their results were stunning, against all odds. Their model showed that an uplink is feasible. Here's why this is a game-changer: creating entangled photons is the hard part, requiring a lot of power and complex equipment. If you do that on the ground, you have access to more power. It's easier to maintain and upgrade the hardware, and you can generate much stronger signals to begin with. The satellite, in this scenario, becomes much simpler and cheaper. It doesn't need to generate trillions of photons to overcome signal loss on the way down. Instead, it just needs a small, lightweight optical unit to receive the two photons from Earth, see if they've interfered, and report the result. This makes the whole system more practical and scalable. We could use networks of small, low-orbit satellites to connect quantum computers across continents. Think of it like this: the current quantum satellites are like sending a secret, coded postcard. The new uplink method is like building the superhighway for a global quantum internet. Professor Devitt compares quantum entanglement to electricity. In the future, he says, we won't think about how it's generated or transmitted. We'll just plug our quantum devices into a network and use the entanglement it provides, just like we plug a toaster into an outlet. The next steps could involve testing this concept with drones or high-altitude balloons before moving on to satellites. This research doesn't just solve a technical problem. It opens the door to a future where quantum computers aren't isolated islands of processing power, but a connected, global network, ready to tackle problems we can't even imagine today. The impossible is looking more and more possible. Thanks for watching. If you're fascinated by the future of technology, make sure to like this video and subscribe for more deep dives into the science that is shaping our world.